Okay, so today we are going to go for chapter 3 on linear momentum. Okay, so this particular study is a study based on Bernoulli equation, but we have some additional parts inside of it. Okay, and for Newton's second law, this is basically based on the 3 Newton's law that we have. Okay, remember from the Newton's first law, it states that the body at rest remains at rest and body in motion remains in motion. Okay, at the same velocity in a straight path when the force acting on it is 0. So it means over here, if a body is not having any force acting towards it, it will stay as it is, or whether it is at rest or it is moving in a certain velocity on a straight path without having a change in velocity or without having a change in acceleration. Okay, so number 2, the Newton's second law states that the acceleration of a body is proportional to the net force acting on it. So, if a body is accelerating, it is based on the force acting towards it. Remember, Newton's first law said that we don't have any movement, change of movement, or it will stay static for a body if you don't have any force. Once we add a force towards the body, okay, acceleration of the body is proportional to the net force acting on it, and it is inversely proportional to its mass. What does it mean by this is, okay, acceleration, it is proportional to the force, it is inversely proportional to the mass. It means the bigger the force acting towards the body, the faster the acceleration. The higher the mass of a body, the slower the acceleration. Okay, so that's the idea of it. So Newton's third law states that when a body exerts a force on a second body, the second body exerts an equal and opposite force on the first. This is an idea of force acting towards hydrostatic force. For example, force acting towards the surface of the tank or a surface of a wall, the wall will have the same amount of force acting towards it so that the ball will not buckle or break down. Okay, so what we are going for is this particular law, which is the second law. All right, so Newton's first law is used usually for a study of static, and Newton's second law is used for the study of linear momentum. Right. So the idea for Newton's second law is coming from F equals to ma. So a lot of idea for force and acceleration comes from this equation. Force equals to m times a. The arrow over here means that this is sensitive to the direction of the force. All right, so remember, going to the right is positive, going to the left is negative. So this arrow shows that we are sensitive towards direction. Okay, so what happened here is, if we can rearrange the equation, we will get the equation in terms of m dv over dt. So when you have a dt down here, it means that the study is on in terms of rate of time, okay? And it will become dmv over dt, okay? So in other way to do this calculation or equation is f equals to ma equals to m times v, velocity, over time. Okay, remember, velocity is in the unit of meter per second. Acceleration is meter per second square. So in order to get the second square here from second, so it means velocity divided by time. Okay, so if we change it in terms of m over t multiplied by v, mass divided by time, so you will get F equals to mass flow rate multiplied by velocity. Okay, so why is it this way? Because remember, mass flow rate, the unit is kilogram per second, meaning it is mass divided by time. So that's why if you have this study, okay, F equals of ma is a typical force calculation. F equals to m dot v over here, or mass flow rate, times v is linear momentum. Okay, so the product of mass and velocity of body is called linear momentum. The momentum of a rigid body of mass moving with velocity is, okay, So therefore, in fluid mechanics, Newton's second law is usually referred to as the linear momentum equation. So normally when we talk about Newton's second law, so this will be the equation for it, right? Okay, so what happened here? Conservation of momentum principle. Okay, the momentum of a system remains constant only when the net force acting on it is zero. Meaning, if the force is not changing, okay, and it is zero, so the momentum will be the same. But once you change the force acting towards it, so the momentum will be different. Okay. All right. So whenever we have a linear momentum equation, remember movement of liquid can be in straight line or a straight path like this. Okay. Or sometimes it can be in terms of a circle like this. Right? Circulation like this. In order for us to understand that circulation, so later on we will learn about the idea of angular momentum. But right now we are going into linear momentum first, and then we'll come back to angular momentum later. Okay. So the equation for angular momentum is practically on moment, but this one will be introduced later after the end of linear momentum. Any problem with momentum, guys?
No.
No.
Okay. All right. So choosing a control volume over here, okay, a control volume can be selected as any arbitrary region. Okay, so this is one part of the study that we have to know. The idea for this is control volume. Okay, a control volume is a way for us to study a certain amount of space or arbitrary region in space through which flows and its bounding control surface can be fixed, moving and even deforming. Okay, why we are learning control volume? Because we want to study only a certain part of a system usually. Okay, so to make sure that the study is only localized to that particular part, we use a control volume idea. Okay, so many systems involve stationary hardware firmly fixed to a stationary surface. Such systems are best analyzed using fixed control volume. When analyzing flow systems that are moving or deforming, it is usually more convenient to allow the control volume to move or deform. Right, so what we have here is we have three different kind of control volume. Number one is fixed, meaning everything is fixed, nothing is changing, but the study that we are going for is between this part to this part. So usually we do dotted lines over here, okay, so that we will have the control volume. Okay, or as we learned in chapter 1, this is the boundary of the system. Okay, so what it means over here is the study that we are going to do after this will only focus on this part and this part. So we might have a longer hose, we might have a hose that is connected to other things before, but we don't want to connect it together in the study. So we study only this part. For the second one, this is when you have a moving control volume, meaning the study of the volume is in this boundary over here, but we are assured that when you have aircraft moving in the air, it will be moving from one point to the other. So this is what considered to be a moving control volume. The last one is deforming control volume. This is when the volume is changing. Okay, so volume of will change. It means that sometimes it is bigger, sometimes it is smaller. For this particular case, this piston is moving up and down, meaning volume will be bigger and smaller through time. So because of that, we need a control volume that is based on the idea of change of volume over here. So the control volume is deforming. Okay. All right. So the application of linear momentum. All right. So the only way for us to study about linear momentum is through a question. Okay. Because if you don't do any question, it's hard for you to do any equation for the system. All right. So now I want you guys to read out the question first, this part. Okay. And then we will try and do this question in my slides. Okay. All right. Or I can just do this question here. Okay, so please read out the question here. Exit velocity V2. Okay, so what I need you guys to do is, I want you to find what is V2. Okay, I give you 5 minutes to find it. Okay ke? Can you see this? Oh no.
Yes, sir.
Wait, sorry want to keep your attention. Okay. You guys are seeing this picture over here, application of linear momentum, is it?
Yes, sir.
Okay, so let me take this picture and bring it to my slides, and then we can continue from there. Okay, give me a moment. Okay, let me share to you my slides. All right, can you see it?
Yes, sir.
Okay, so I need you guys to do one thing here first, and then we will continue with the calculation. All right, so this is the application of linear momentum. Okay, so please read the question over here, and the question over here requires you to study about okay, let me find out. Okay, a reducing elbow is used to deflect water flow at a rate of 14 kilogram per second. Okay, so this question is based on mass flow rate. All right, in a horizontal pipe upward 30 degrees, so 30 degree over here, while accelerating it. So the elbow discharges water into the atmosphere. The cross-sectional area of the elbow is 113 centimeters square here, 0.1. Okay, and the inlet at the inlet and 7 centimeters square here at 0.2. At the outlet, the elevation difference between the center of the outlet and the inlet is 30 cm. So this is the elevation difference. The weight of the elbow and water is considered negligible. So determine A, the gauge pressure at the center of the inlet of the elbow, and B, the anchoring force needed to hold the elbow in place. Okay, what I need you to do right now is, number one, using Bernoulli equation, try and find the pressure at point 1. Okay, you guys have studied about Bernoulli equation before. From the information given to you, I want you guys to find out what is the pressure at point 1. Okay, everyone? Okay.
Okay, sir.
Okay, kita tak masuk lagi linear momentum, tapi we want you to do the Bernoulli equation calculation first. I give you around 5 minutes. Okay, all the informations about it is there. So any answers from anyone? Anyone? Any answers? Sunyi sepinya. So let me check. Cornelius, are you there?
Belum sir, masih calculating.
Masih calculating. Dah sampai mana?
Nak ni lah.
Ya, okay. Anyone yang dah settle? Nur Izzati, are you done? Nur Izzati, are you there? Izzati. Wow. Everyone is shy today. Zul Hazim, are you there? Zul Hazim. No answers. Muhammad Mustaqim, are you there?
Yes, sir.
Okay, do you get the answer for this question?
Not yet, sir.
Not yet, sir. Okay, so let me help you guys on this. All right, so before that, this is a bit of an idea of linear momentum, okay? So based on Newton's second law, the acceleration of a body is proportional to the net force and inversely proportional to mass, okay? So we did this before. This is how we change from force in terms of MA into this condition, which is our linear momentum study, okay? Momentum can be divided into two. One is linear, okay? Another one is angular. So linear, it means that the movement that we are going for is in linear condition, which is either horizontal, vertical, but it is a straight line, okay? However, if we go for angular, angular is when you have a spinning, for example here, you use water, you water the grass over the system by having an angular condition. So what happened here is, okay, we have, for example, a sprinkler, okay. So water is coming out from the sprinkler like this. So what will happen, since the water is pushing to the back, it will spin counterclockwise. Okay, so that's the idea of it. All right, so when can you see momentum study? Okay, momentum is a study that you can usually see sometimes when you are dealing with or if you can, you watch something from the internet or from the movie where we have rocket launching or satellite launching, okay, where you can see, for example, I'm not a good sketcher, but you get the idea. Maybe this is a rocket or a system that you want to send, okay, up to the atmosphere, to the sky or to the space, okay, like this. All right. So when will you see the idea of linear momentum? Here, when we have thrust coming out, okay, when you start the combustion and you have all the thrust pushing downward, okay, thrust is a force coming out from a system like this. So what happened? All the thrust coming from the combustion from the engine and the rocket will push downward. But what happened to the body of the rocket? It will be pushing upward. Okay. So what happened here? The thrust from combustion, okay, is pushing downward. Okay. However, the body of a system that we are using here, or the rocket itself, or the satellite itself, is moving upward. So what you have here is, when you have a force of liquid pushing to another direction, okay, the body will tend to move to other direction. Okay, so this is an example of it. Okay, the second example, for example, if you have your tap at home, all right. Okay, so this is your pipe. So this is tap at home. Okay, usually you connect it with a hose. So the hose is on the floor, for example, and try and speed up the liquid coming out from here, increase the volume flow rate coming out from here, you will see that the hose will be moving left or right. Why? Because water is coming out from the hose at a certain velocity, and the hose, because it is elastic, okay, due to this, it will create a movement to the body, or for our example here, hose, okay, and it will be moving upwards, downwards, or sideways, okay, due to the condition where the liquid is coming out from a pipe. So what we can see over here is, whenever we have liquid coming out at a certain velocity to one direction of the study, usually it will provide an impact towards the body, and the body will be moving to the other direction of the body. Okay, the same idea for here, the same idea for here also. So each time you want to design something, for example, an angular momentum here, all right? So you want to make sure that the body is all the movement of liquid, all right? So to do the study, we do the study in terms of an elbow here. So the picture that you see over here is an elbow. So what do we have before the elbow? For example, this is liquid coming from the pipe. Okay, so the liquid comes in at a certain area, and then it comes out at a certain area also. So this one you can see it is becoming smaller. So the elbow over here is a reducing elbow. What we are doing right now is we combine two conditions. Number one, liquid is moving from bigger space area or to a smaller one. So we are changing the area. We are actually changing the velocity. Number two, we have an elbow here, means that the flow is hitting a certain part of the elbow here due to the angle of 30 degrees over here. And when the water comes out from this side, what will happen? Water comes out, it will affect our body that is holding the water. Okay, so if the water is going out this way, the body might be changing in direction also. So what we need to do is, if we have to fix this body over here, it needs to be fixed at a certain amount of force. Okay, that's why when you have for example, this picture, any picture like that. Okay, no. So for example, if you have the hose over here and also your, okay, pili kat sini. So what do we have over here? Usually you will have a thread, okay, and then this is a hole with a thread also. So we want to put it in by spinning our pipe into the circle over here. Okay, so this thread creates or okay, a holding force for the body. Okay, if not, if you leave it this way, you just fix it in without the thread over here. When the water is fast, it comes out fast. This body will be shaking or vibrating, and it can open up from the hole over here. Faham ke maksud saya ni?
Faham sir.
Faham So kalau awak ada pipe, pilih pipe tu, awak nak masukkan tu, perasan kan dia ada macam thread tu kan? Okay. So yang kita letak getah putih atau apa tu, white tape tu, and then kita masukkan dalam lubang dia tu, kita spin lagi kan, nak bagi dia tutup habis, betul? So what happened there is, we want to make staying at the same condition, kita tak nak dia bergerak-gerak, so we fit in together like that. Okay, so why? Because when water comes out from the pipe, okay, there will be an effect towards the body that we have. Okay, for example here, so this is the question. So what we want to know right now is, at the end of the study, we want to understand what will be the amount of force acting towards the body. Okay, so the force tu is called as FRZ and FRY ataupun FRX. Okay, FRZ and FRX. Okay, so these two is important. Why? Because by having FRZ and FRX, we can find out what is FR. Okay, so what is this? What are these two names for this? We call it as anchoring force. Anchoring forces. And what are the function of the anchoring forces? Okay, so the function of the anchoring forces is the amount of forces required to hold the elbow or body from moving due to momentum. Okay, so the amount of forces required to hold the elbow or body from moving due to momentum. So that's the idea of anchoring forces. Okay, so what happened here? If water is coming out from this side, okay, the body will be moving backwards to the back. Okay, so we want to study what is the force acting towards the body and how we want to counter it. So the anchoring force over here is also called as a counter force. Okay, so to withhold the body from moving due to the liquid moving out from the system. Okay. Dulu ada yang siapa-siapa cadet bomber ke? Ada Awak cadet bomber pernah guna hose dia kan yang boleh tarik bagi air pergi jauh and then pergi dekat tu kan? Correct? Okay. Berapa ramai orang diperlukan untuk pegang benda tu?
Tak ingat lah, tapi ramai lah.
Ramai kan? Sebab apa? Bila
dia-
air keluar daripada nozzle tu kan, awak boleh control dia pergi jauh dengan dekat kan? Awak akan rasa macam tersentak ke belakang, correct?
Betul.
Betul. What happen over there is liquid is moving at very high velocity. Dia akan create that linear momentum, and yang akan terima that linear momentum is the pipe and also the person who are holding the pipe. Okay. So awak pun paksa ramai-ramai supaya awak sekali pun tak tergerak ke belakang. So that's the idea of it. Thank you. And also, if you see people or movie where people are using pistols, okay, so pistol is another idea of linear momentum. When you have the bullet, but instead of liquid, now it's bullet lah. Okay, so it's not fluid mechanics, but it's still the same idea. The bullet is coming out from the barrel, so your hand will be moving backwards also. Okay, if you are cadet askar ke, macam cadet-cadet Persatuan Bersatu Malaysia ke, Kadet Bersatu Malaysia, boleh main, dapat diberi peluang untuk tembak pakai M16 dan sebagainya, awak akan perasan dia akan suruh letak macam tepat letak ni kat bahu okay, before you shoot anything. Why? Kita tak nak dia tersentak ke belakang so bahu tu akan hold dia daripada bergerak. If not, awak akan ada condition where senapang awak akan bergerak atas bawah atau kiri kanan when the bullet comes out from the barrel. So that's an idea of linear momentum also. But for us, since we are dealing with liquid, so we are dealing with liquid only. We don't have any object in terms of solid object. Okay. So now, to do the calculation first, what we have to do is a reducing elbow is used to deflect water at a rate. So we have mass flow rate in terms of 14 kilogram per second. Right? Since this is water, we will assume the density of water should equal to 1000 kg per meter cube. So we assume okay, the elbow discharges water in the atmosphere. The cross-sectional area of the elbow is 113 centimeter square. So A1, okay, this part, A1 is equal to 113 cm square. Make sure you change it into meter square. So 1 meter square is equal to 100 cube centimeter. Oh, sorry. 1 meter square is equal to 100 square. Okay. If you don't want to get confused, you just have to do it this way. 1 meter, 100 centimeter times 1 meter, 100 centimeter. So 113. So you get the answer to be 0.0113 meter square. Okay, so A2 is 7 centimeter square. So multiply by 1 meter square, 100 square centimeter square. So it is equal to 0.7 times 10 to the power of -3 meter square. Alright, so we get the area first. Okay, the elevation difference between center of the outlet and the inlet is 30 cm. So you can see over here 0.2, 0.1. So Z2 minus Z1 is equal to 30 cm or equals to 0.3 meter. Okay, the weight is negligible. Determine A, the gauge pressure at the center of the inlet. Okay, so first, this is a question of Bernoulli. So remember, if you get a question for linear momentum, number 1, use Bernoulli equation and continuity equation. To find P gauge or to find out velocity. All right. So first, we can see over here, the question asks us what is the gauge pressure. So in terms of pressure, what you need to do, we don't have any manometer. So we need to use Bernoulli equation. So here, P1 over rho G plus Z1, P1 square over 2G equals to P2 over rho G plus Z2 plus V2 square over 2G. Okay, so P1, Z1, V1, P2, Z2, P2. So we check on things that we can cancel out. Number 1, P1 cannot, V1 cannot cancel out. Z1, can we cancel out? Considering this is lower than this elevation, we can cancel out. For this study, the elevation starts at the middle of your pipe. Okay, ends at your middle of the pipe also. So 0.1 at the middle, this will be the lowest part. So this is the reference point. So we assume it to be 0. Okay, Z2 over here will be 30 cm. Alright, V2 available, but P2 will not be available because it is meeting the atmosphere. Once again, what we are searching for is just gauge pressure. So from there, we can get P1 is equal to V2 square minus V1 square G, alright, plus Z2, and then multiply by rho G. Okay, so we can discover over here that we don't have the number for V1 and V2. that's the reason why they are giving you the mass flow rate. So mass flow rate is equal to rho 1, or the rho should be the same for both sides because we are using water. So we just find out what is the velocity. Mass flow rate is equals to rho A V1. Okay. All right, to find out V1, it is equal to mass flow rate divided by rho A. So equals to 14, 1000. The area is given here, 0.0113. So V1 is equal to 1.239. Okay, so 1.24 meter per second. All right, how about V2? V2 is equal to mass flow rate divided by rho A2. So equals to 14 divided by 1000 divided by 0.7 times 10 to the power of negative 3. So it will become 20 meter per second. All right, so we have the number here. So what we do is we put in a number in the calculation. So 20 square minus 1.24 square. Okay, and then plus Z2 is 0.3 and then multiply by rho 1000 times 9.81. Okay, so that is for P1. So the answer is P1 is equal to 'Okay, so we get the answer to be 202.174.2 Pascal. So that will be the answer for question 1. Is everyone okay with this?
Okay, sir.
Okay. All right. So we get the idea here. So this is a normal Bernoulli equation. Nothing different from what we learned before. Just basic Bernoulli equation.
Sir,
Okay.
yang Z1 tu kan, dia
Hmm.
bukan dia kena cancel dengan P2 bukan Z2
Z1 dengan Z2. No, Z1 is just cancel lah, 0. It's not cancelled
Yang
out with anything else. Yeah.
yang row 2 over row G tu.
Row 2 over P2. P2 here.
Oh, P2.
Over
P2.
G. This one is cancelled out because this is atmosphere, correct here?
Oh,
PETM.
okay.
So once again, we are using gauge pressure for chapter 3. So anything outside of the surface, P is equal to 0. Okay?
Okay, sir.
All right. Okay, now this is just basic Bernoulli equation. Now we will enter linear momentum calculation. Okay, so all right, so let me copy this. Okay. Right, so the same picture as just now. So we are going to do that. All right. So now we will enter the idea of linear momentum. Okay. So the idea of linear momentum is we have inlet and we have outlet of a system. All right. So usually the inlet is denoted as 1. outlet as 2, or either 1 or 2, or inlet outlet I and O. Okay. All right. So in terms of linear momentum, in order for us to use this picture and to do the calculation, first we need to add on some drawings to the system. Okay, what drawings do we have to add? Okay, we have two drawings. Number one, I use different color pens over here. Okay, number one, okay, this arrow over here represents the arrow of liquid flow. Okay, so liquid flow, it means over here, the flow of liquid will be like this. Okay, so this will be the arrow for momentum. Right, so over here, this arrow is also represented by m dot v1. Okay, so how do you decide the arrow is moving to which side? Okay, just check. The direction of flow is from left to right, so the arrow is from left to right. Direction of flow is from bottom to the top to the right. We will also draw an arrow like this, which is m dot v2. Right, that's number one. Number two, we have a second arrow. I use a different color. Okay, this arrow is called, okay, liquid flow momentum. So this arrow is called liquid flow momentum. All right, we change it and name it as pressure. Okay, and the pressure will be like this. Okay, the flow of system going to the right will be this way. The pressure will also come into the system, so it will become P1A1. So pressure times area, which is equals to force. All right. So green color is for pressure, blue color is for liquid flow. Right. Okay, in the next part, okay, this part, we must have a pressure that comes into the system. So this is P2A2. Right? So we have P1A1 coming into the system. Coming into the system also is P2A2. Direction is coming into the system elbow. For a question like this, it's the same also. P1A1 into the system, P2A2 coming into the system. Right? This question is the same. P1A1 coming into the system, P2A2 will go into the system. So for every calculation for linear momentum, keep on doing it this way. Liquid flow, m dot v1 and m dot v2 follows the flow of liquid. Pressure times area will be acting inwards towards the body of the system. Is it okay? Everyone understand this?
Yes, sir.
Yes.
Okay. So now we will do it this way. Okay, the first thing is number one, okay, we have this condition over here. So for me, what I'm going to do is, usually for this particular study, I will create an arrow like this. A table like this. Okay, the table on the left is called force. Table on the right we'll call as momentum. Okay, force over here is in terms of P times A. Momentum over here is in terms of mass flow rate times V. Okay, so force over here, so what we will do is, right, so we always follow the idea of going upward is positive Y, going to the right is positive X. Okay, so what do we do here is, first, check on this question, check on P1A1 and P2A2. So P1A1, is it moving to the right or to the left? I need someone to help me.
Right.
To the right.
To the right. Okay, siapa yang tengah cakap ni? Yang suara perempuan ni, wanita ni?
Saya, sir.
Siapa tu? Saya tu.
Alani.
Alani. Okay, Alani tolong saya. So P1, A1 is to the right, correct? So
Yes.
we add plus P1, oh sorry, before we do that, okay, I need to define what I'm doing right now is summation of force in the x direction equals to 0. Going to the right is positive. So we go and find the x direction first. So P1, A1 to the right. So positive P1, A1. All right. Then P2, A2. Is it to the left or to the right?
To the left.
To the left. So is it positive or negative?
Negative.
Negative P2, A2. Now, is it to the left horizontally or with an angle?
With an angle.
With an angle, okay. So if we draw the angle over here, okay, since down here is 30, here will also be 30 degree. So what you'll have is negative P2, A2 cos 30 degree. And then add up FRX at the back. Okay, so that's how we do this calculation. So first, find out P1, A1, positive or negative, P2, A2, negative or positive based on the direction. If there's an angle here, put a cos over here, and then you add up FRX at the back. Just put it here, okay? And always put it as a plus sign, FRX. Okay, why is that? We are trying to find out what is the anchoring force for this study. All right, on the right side, momentum. So it is equal to actually the momentum. So momentum side, siapa seorang lagi yang bagi jawapan lelaki tadi?
Saya je.
Siapa tu? Nama dia?
Thank you.
Okay. So check on m dot v1 over here to the right. So is it positive?
Positif.
Okay. So m dot v2 to the right also, correct? Positive,
Yes.
but with an angle. All right. So for momentum, what you need to do is, it's different from the idea of force. Force, you just add up. But for momentum, you must have the calculation in terms of m dot, okay, v outlet, which is v2, minus m dot of v inlet, which is v1. Right? Why is it minus over here? Because this is not due to the direction. This is because of the operation. The operation is outlet minus inlet. So that will be the operation. But since both to the right, so both of them is having positive number. Okay, so for example over here, both of them are having the same number. So this positive, this is also positive. If the question is different and the direction is not positive, it will be in a different condition here. Okay, for now, it equal to m dot v2 minus v1. All right, so if everyone okay, I will continue. Okay, what's the next thing that you have to do? Okay, the next thing is, check from this picture, is there anything that we can cancel out? Okay, P1, A1, can you cancel out? No, nothing. P2, A2, can you cancel out? Yes. Why? P2 over here, remember from our study of Bernoulli, since this is atmosphere, P2 is equal to 0. So this cancels out and becomes 0. Okay. M dot V2, V2 is available, V1 is available. So at this point over here, the equation will change into we rearrange the equation. FRX is equal to m dot v2 minus v1, okay, minus p1 a1. So that will be the equation for this particular study. Alright, so if you get the number here, alright, so the number will be consist of positive or negative. If positive, it means the direction of force to withhold the body should be to the right side. If it's negative, the force required to hold the body should be to the left side. Okay, so we do another one in terms of y direction. So somebody else, I need somebody else to help me. Anyone? Oh, nobody eh. Kena memetik nama di sini eh. Okay, Jennifer, are you there?
Yes.
Oh, okay, Jennifer. Can you help me?
Okay. Yes.
Okay. Okay, Jennifer, this is the question here. Sorry, just now. Okay. So I need you to tell me just the idea of positive or negative in terms of y direction. So let me write it down here. Summation of Fy is equal to 0. Going up is positive. All right. So P1A1, is it positive or negative?
Negative.
Negative. It's going to the right, right? Is it going upward or downward?
No.
No. Since there is no upward or downward movement or any angle to the top or to the bottom, so P1A1 is equal to 0. Okay. All right. So why is it equal to 0? Because there is no vertical force. That's why P1A1 is equal to 0. All right. Now, P2A2, going to the top or going to the bottom?
Bottom.
So, is it positive or negative?
Negative.
So, negative P2A2. And since we have an angle 30 degree here, is sine 30 degree. Okay. Now, we have to add another one, which is W here. Okay. Each time we have a liquid and also a body like this, we will have a W going downwards. Okay. And W, since it's always going downward, weight based on gravity, it's always minus W. And then you add up Fry. Okay. If you can see from here and from here, the difference is this part. Okay. We have P1A1, P2A2, but we have the addition of W. So W in the question is said to be considered to be negligible. Negligible means that W should equal to 0. Okay. P2A2, once again, since it is meeting the atmosphere, correct? So P2A2 will also becomes 0. Okay. Okay, Jennifer, are you there?
Yes.
All right. So for momentum, we continue with the momentum. Okay, m dot v. All right. So m dot v. So m dot v2 is the outlet minus the inlet. So m dot v2, is it going to the top or to the bottom?
Top.
Okay, so m dot v2. Okay, before I forget here, I'm doing a mistake here. All right. Thank you, Jennifer. Let me clean this up first. Okay, I'm doing a mistake here. So make sure you double check it again. Okay, this should not be m dot v2. It should be m dot v2 cos theta. All right. So this will not be this way. It will become, sorry, it's my fault. So the equation should be m dot V2 cos 30 degree minus M dot V1. Because there's an angle here, I forgot about the angle here. So let me cancel out this. So FRX should equal to M dot V2 cos 30 degree minus V1. Sorry just now saya terlepas pandang, minus P1 A1. Okay, so for this side, it's the same thing also. Make sure don't do a careless mistake like me, okay. So what you need to do is, here, V2 over here is with an angle. So this is sine 30 degree. And then minus V1 over here, okay. So if you check for V1, do we have any vertical movement of flow over here? No, only horizontal. So V1 should equal to 0. Alright, so the equation for this study will be equal to, I cannot erase that. So the equation with this study will equal to Fry equals to M dot V2 sine 30 degree. Okay. And then we find out what is FRX or FRY. Okay. So it can either be Z or BY. It doesn't matter as long as you define it. All right. So it is also here we have FRX and FRY. So how do you find out what is the amount of FR of the study? Okay. So at the end, when you find out what is FRY, FRX, so FR is equal to FRY square plus FRX square and the square root of it. Okay. And the angle of our calculation, okay, theta is equal to inverse tan FRY divided by FRX. Okay, so that will be it. All right, so if you check on this, what will happen? We want to know the result from this. Okay, if you fill in the numbers, it will show to you that what is the amount of FRX together with the positive or negative. Okay, positive or negative sign will give you the idea whether it is the force required is downwards or forward. Okay, it depends on whether it is Y or X direction. Okay, so any question on this?
No, sir.
No. Okay, I need you guys to fill in the numbers here and try to get the answer. Then we are going to stop with the class. Okay. So anyone boleh tolong kirakan jawapan dia? I will try and calculate together with you. Based on this calculation, FRX, so here, FRX is equal to so mass flow rate is 14, P2 is 20 meter per second, minus V1 which is 1.24, minus P1 202,174, Okay, I guess. Alright. Multiply by area 1, which is okay, so 0.113. 0.13. So FRX,
Negatif je.
so the answer will be negative, is it? Okay.
2059.44.
2059.44. But
Negatif tu tak payah saya.
negative, it will be here. Negative, eh?
Ah.
So negative 2059.44. Right, let me rewrite it again. Okay, what does it mean by this is the force required to hold the body from moving is a negative force. So it is acting like this. If I want to hold the body, I need to create a force that is acting this way. Bermaksud, water is moving this way. Since the water is hitting the surface of your elbow here, it is trying to push the elbow to the right. Okay, to hold the elbow from moving to the right, we need a force acting to the left. Faham maksudnya? Air lalu kat sini, jumpa dengan body ni, dia akan hit the body, body tu akan ada tendency untuk pergi ke kanan. Okay, so kita perlukan counter force to elakkan body tu tadi gerak ke kanan. So the FRX should be in a negative answer like this. Clear?
Clear
Okay.
sir.
So we do the second one, which is FRY. So FRY is equal to okay, saya rasa we don't have any other things over here. So it is equal to 14, 20 sine 30. Okay, so FRY is equal to
140.
114.
140. 140.
Okay, so FRY is equal to 140 Newton. Positive, eh?
Positif sir.
Okay, so positive, it means that this water will move to the right. However, what happens when the water moves to the right, it will force the body to move downward. So to withhold the body from moving downward, we need an FRY that is moving upward like this. Okay, so that's the idea of it. Right, next, usually the anchoring force, meaning we need to find out what is FR. So to find out FR, as usual, we calculate using the equation just now. So FR is equal to FRX square plus FRY square, which is equal to negative 2059.4 square plus 140 square root of it. Okay, so FR should be equal to 2063.75 Newton. Okay, so that will be the FR. Even though they do not ask you what is the number for angle theta, we just find out theta, inverse tan, FV, which is FY lah, FRY. So theta is equal to 3.88 degree. Okay, 889, sorry, 3.9 degree lah. Oh, this is a weird number. But don't worry. Just put whatever that we have here. So 3.89 degree. That will be for the angle theta. So why is it important to find out what is the angle theta over here? Okay, because later on you need to show to us okay, what is the amount of force acting towards the body? Okay, first, Frx is going to the left, so Frx this way. Okay, and then Fry is going to the top. Okay, so Fry is this way. Okay, so you have Fr. So Fr should be this way. So Fr is equal to 2063.75 Newton with an angle theta equals to 3.89 degree. Okay, so if I want to minimize the amount of force acting towards it, I want it to be in Fr. So the Fr will be in a certain angle like this, with an angle of theta. Alright, so in order for me to make sure that the elbow will not pull off from the pipe, so I need to make sure it is holding up to 2059 Newton of force on the X direction and 140 Newton of force in the Y direction. So if I can do it, if I can fix this part so that it does not move, meaning I can bolt it to the wall, for example, so that it does not move up and down, so we will have a very steady elbow that will